Hello everyone, welcome to my channel. I think we have a new circuit here. We have this LED blue and LED red. Let us see the circuit. The circuit of this red LED is this. This is a transistor circuit design, no pull down resistor. And this is the circuit diagram of this circuit. We have 5-volt supply, switch, single pole, single throw, resistor, LED, transistor C2878 NPN, and then a resistor in the base. This is our previous circuit, so let's just make a quick review of the current flows in the circuit. We are using an NPN C2878 NPN transistor. Current flows when you close the switch, voltage supply to the resistor, LED, transistor, and to the ground. Also here to the base, transistor, and to the ground. And we calculated all the values because this is our previous circuit. And now we have a new circuit here, the blue LED, and the circuit is this. Transistor Circuit PNP. And this is the circuit diagram. We have 5-volt supply, switch, resistor, LED red, transistor BC557C, PNP, and a base resistor. As we have said, in the NPN BJT transistor, current flows here to the ground, also here. In this PNP transistor, current flows here, collector transistor to the ground, also here in the base transistor to the resistor to the ground. In here we are connecting the power supply to the base. But here, this is the connection, resistor to the ground, because this is PNP transistor. We have given data here. Voltage rating of the LED 2 volts, current rating 0.02 ampere, and it is given in the datasheet of an LED. Also a transistor current gain here is 320 HFE, and a voltage base to emitter on voltage is negative 0.7 volts. Negative because this is PNP. And we have voltage collector to emitter at saturation of the transistor is negative 0.25 volts, also given in the datasheet of the transistor. First, this resistor is used to protect the LED from burning. Also, this resistor is used to protect the transistor from damaging, and also as a base and the bias resistor of the transistor to the ground. Let us calculate the value of RD here using Kirchhoff's voltage law. voltage supply minus voltage drop across the resistor minus the voltage drop across the LED and voltage drop across the emitter to collector of the transistor and to the ground. That is the Kirchhoff's voltage law. First loop here in the pink line. We got now this equation. And the voltage collector to emitter at saturation, collector to emitter, is negative 0.25 volts. In here, negative minus negative equals plus. Calculating the values, we got voltage drop across the resistor of 3.25 volts. Voltage drop across the resistor RD. And using Ohm's law, voltage is equal to current times resistor RD now is equal to voltage drop 3.25 and the current 0.02 ampere. That is given in the data sheet of the LED. Current in the LED is the same as the current in the resistor since they are in series. That is according to Ohm's law. Current in series is equal. So, calculating the values, we got 162.5 ohms. I am using 220 ohms. That is my available resistor. Let us find the current across the base, or IB, base current. This one, by using a current gain formula of the transistor. HFE is equal to IC over IB. Crisscrossing transposition, IB is equal to IC over HFE, which is also equal to IC over beta. HFE is also equal to beta, same formula. IB now is equal to collector current, which is here. The current at the collector is equal to the current in the LED and the current in the resistor. That is given in the data sheet of the LED, 0.02 ampere. And the beta and the HFE is 320, given also in the data sheet of the transistor. We get now IB, base current of 0.0000625 ampere, a very small current to turn on the transistor. So we know the base current. Now we're going to calculate the voltage drop across the base resistor here, RB, using Kirchhoff's voltage law. At RB, just follow the orange line here, and that is the KVL. Voltage supply minus the voltage drop across the resistor, voltage drop across the LED, voltage drop across the transistor emitter to base, voltage drop across the base resistor is equal to 0. Because according to Kirchhoff's, all voltages in a loop, closed loop, is equal to 0. Now we have this equation. Voltage supply minus voltage drop, resistor, LED, voltage at the base to emitter on. That is the on voltage of the transistor. That is given in the data sheet, that is negative 0.7 volts. Because we are using PNP, that's why it is negative. Substituting all the values, we know this voltage RD, we know also the LED and the onboard voltage of negative. Since this is negative, negative equals positive, and we got 0.52 volts voltage drop of the base resistor. Using Ohm's law, we find the value of the resistor RB. B is equal to IR according to Ohms, and we know the voltage drop across the resistor 0.52 and the base current, since we know that is in here 0.000625 ampere, and we got 8,320 ohms. Converting it to kilo ohms, 8.320 kilo ohms, but I use 8.3 kilo ohms. That's my available resistor. And we have this BC557C pinout, CBE. That is the actual component, and this is the symbol of PNP BC557C. E, emitter, base, collector. We have features here: PNP bipolar junction transistor BC557C. So this design, we're using BC557C, and we're using one power supply, and the PNP transistor is used as a switch operating in saturation mode. And we have the parts here: voltage supply 220 ohms, and this 8.3 kilo ohms. 5K plus 3.3 kilo ohms is 8.3 kilo ohms. Since we're using only two resistor, 220 and 8.3 kilo ohms. LED blue, 10 mm in size. Transistor BC557C, and a perf board. We know the parts, and now we come to our final circuit here. We have power supply, switch, value of the resistor in the collector 220 ohms, LED blue, transistor 557, base resistor of 8.3 kilo ohms, and this is the circuit diagram. And we have this layout. We have three resistors, that one, and we have this transistor, that black one, and we have the LED blue, and it's working. I think our calculation is working because the final circuit is working. Let us check. Turn off the power. It will turn off. Turn on. It will turn on. So the circuit is working. This is our final circuit. And thank you for watching the video, and bye bye.